Hello, I'm JW, and in this video we'll be having a look at the voltage operated earth leakage circuit breakers. Here's an older GEC example, and then here's the Crabtree version. And we're looking at how these things actually work and the problems which these things have. Now, these haven't been used in the UK since the early 1980s and have been largely replaced these days with RCDs. Now, to be clear, these things are not RCDs. They work in a totally different way, despite the fact they have the test button on the front. If you've still got one of these in your house, it's really high time it was replaced. So these things have a number of significant problems, the main one being that they don't actually protect people who come into contact with a live wire. Now, before we look at the devices themselves, it's a quick overview of how the electricity supply would actually come into a typical building. First of all, you're going to have a transformer, some sort of core. Over this side, you're going to have probably 6 kV or 11,000 volts. And the transformer there is just there to reduce the voltage to typically 230 volts. In other countries, of course, that may be somewhat lower than that, 120. Typically in the UK, though, it's supposed to be 230. Usually it ends up being around the 240 or so mark. And from the transformer, you've got the 2 wires. And as it sits there, the 2 wires are just sitting there. There's no reference to ground or anything else. And we'll call the wires, we've got line at the top there, and we can call the other one neutral. But of course, the neutral wire isn't actually neutral at the moment because we haven't actually connected it to anything. Currently what we've got there is basically an isolating transformer, so got 230 volts between the wires, but currently nothing is actually referenced to ground. So here's the ground here, and all I need to do is put a connection from the neutral to the ground. And this is a typical arrangement so that if somebody was standing on the ground and touches the neutral, they're not going to get a shock because there's no voltage here because it's of course connected directly. But if you're standing on the ground and touch the live, you're going to get 230 volts through your body, causing serious injury and death. Now, inside your house, those 2 wires will continue in, and those will go to your appliances or whatever you've got inside your house. Now, the earth connection can be done in a couple of ways. The first way is that you've got a separate wire which goes all the way back to the earthing point at the transformer. Now, in this case, because it's a solid copper or other metal path, the resistance of that, or the impedance of it more correctly, is going to be extremely low. And if you shorted out the main, let's say there was a fault between the live and the earth, a substantial amount of electricity is going to flow all the way through here, through the there, back through to the earth and back to the transformer. And so because it's all a solid metallic path, that's going to have a very low impedance. A typical sort of value for something in the UK would be in the order of, say, 0.5 ohms. Sometimes maybe more, a bit less, but that wouldn't be too surprising. So the amount of current that flow can easily be calculated using Ohm's law, which voltage is current times resistance, or in the case if we've already got the resistance, that can need to be rearranged. So we've got the current is equal to the voltage divided by the resistance. So in this case we've got 230 volts divided by 0.5 ohms. So the total current which will flow will be 460 amps. Now, of course, this is only theoretical, and in the real world, where the electricity comes into your house, you will have a fuse, and then there'll be other fuses in your fuse box, and certainly in the UK in the plug of the appliance that the fault has been created in. If it was the one in the plug, say it might have a rating of say 13 amps. Now, pretty obviously, if you're going to put 460 amps through a 13 amp fuse, that fuse is going to blow pretty much instantly and the circuit will be disconnected, therefore making it safe. Of course, that's exactly what you want to happen. That's the whole point of having the fuse and having this return path with a very low impedance. Now this is a typical setup, but there is another way, in which case you don't get a metallic path back to the transformer. You would typically find this on a supply which came in overhead, but it can be underground or via any means, in fact. And all you get from the supply company is the line and the neutral wires. Because you don't have an earth connection, which clearly is unsafe, because then any kind of fault in the installation, you're going to get an electric shock off the metal case of your washing machine or whatever else has got the fault inside. So what you do is put an earth electrode or earth rod into the ground, and then from here that will become your earth connection. Now in this case the return path is going to be via the earth electrode, which of course is actually in the ground, so this mass of the ground is going to form a major part of the actual return path for the current. Now all of this is still the copper we had before, so very low impedance, but from here to here it's going to be extremely high compared to this. Typically if you've got an electrode in the ground and you manage to get in the 100 ohms range, it'd be considered to be doing quite well. In this case, let's consider we've had a impedance here of 40 ohms, which would be considered to be actually rather good. And we can put that into the equation here, so voltage is the same and the resistance will be 40. So the fault current in this case is 230 divided by 40, which is 5.75 amps, or just under 6 amps. Now there's a big problem here. 13 amp fuse, 6 amps or so going through it, nothing is going to happen. That current will just continue to flow around here forever. Nothing will happen at all. And even if you had, say, a lighting circuit, which in the UK would typically be fused at, say, 5 amps, or sometimes with a 6 amp circuit breaker, 5.75 amps on a 5 amp fuse, again it won't actually blow, because a 5 amp fuse can actually take rather more than that. And even if you did, it's going to take literally hours and hours for this thing to slowly heat up and eventually melt through. During which time, all of the exposed metalwork where the fault is going to be at or near 230 volts. Quite easily, if someone touches it, they're going to get a shock and possibly get killed. Not to mention the colossal waste of electricity just continuously flowing around here at 6 amps or so all the time. This thing will be sizzling away in the ground like anything. Clearly a bad situation that you don't want to happen. And this is, of course, where things like the earth leakage circuit breakers come into use. All these things do is detect the voltage on the earth conductor here. So if we were to install one in this particular installation, it would go in here. And the sensing part of this is simply a magnetic coil. When you get a certain voltage across this, it will of course produce a magnetic field. And that magnetic field can then pull in a piece of metal, and that's what will trip off the switch on your circuit breaker. So we'll have to have a look now what's actually inside one of these things and how they are intended to actually operate. Now the first thing we've got, of course, is a switch, because clearly that's the whole point of the thing. It can switch the incoming supply on and off. Most of them were double pole like this. You've got the 2 incoming terminals and of course the corresponding 2 outgoing terminals. So all we've got really is simply a double pole switch, some power coming in, some kind of switch in there, and the power going out. And obviously these will be the neutral and line like that. So all this does simply switches on and off. When it's on, power can flow through into the installation, and of course when it's off, the power does not. Now, as showed previously, we do need some kind of mechanism to automatically trip this thing, and that is simply a magnetic coil. And we just draw that over here. Let's do this as a box, so that's easier. And when this is magnetised, it will pull on a piece of metal. We can put the piece of metal in here somewhere, and that's mechanically connected to the double pole switch, so that when the coil is energised, magnetic forces pull on a bit of metal, and that will disconnect the switch. And the switch is generally spring loaded, so that if it's just sitting there, a slight press on the lever and it will snap off and remain in that position until someone turns it on again. Now the coil, as I saw before, is just simply connected to, first of all, the two connections there, and we're going to have the top here connected to the earth electrode in the ground, and then the other side is connected to the installation earth, which was generally referred to as the frame of the installation. So when there's a fault between, say, the line and the earth in the installation, current will flow through via the coil back to the electrode in the ground, get a voltage across the coil, and of course that's what will trip and disconnect the supply. Now as it stands, that thing's perfectly fine, that will actually work, but of course it's not very useful because we can't actually confirm that it's working, and certainly in the case of this type of installation it all relies on the electrode in the ground being of a suitably low impedance and of course still being connected. If that was to be disconnected for some reason, no one would ever know until some fault occurred and people were killed or injured. So these devices, you can see on this particular one, has a yellow button there, which is a test button, and all the test button does is it fits in here. So we've still got our connection to the frame of the installation, but what's actually in here now is a switch with the other connection over here, and that's connected via a resistor to the line conductor there. Now in the normal position, of course, it is connected across there like that, so that's exactly what we had before. When you actually press the test button, it's disconnected from the installation earth and it's connected across here. This of course will normally close, so again you've got line coming in, so you've got line voltage connected straight across through the coil to the earth electrode, so effectively you've created your own temporary fault there. Coil will be energised, supply will be disconnected. It's disconnected from the installation because if it wasn't, if we just had the connection across here, the problem now is that you've got the line coming in via this little resistor through your coil, but you've also connected all of the metalwork in the installation to the line conductor, so you'll actually get dangerous voltages appearing on the metalwork in the installation. That could be the metal cases of things like washing machines and kettles and other things, and in certain other cases stuff like water pipes and other metallic items. So that's why it's actually a changeover switch, and it's sort of the type that breaks one connection before it makes the other one, and that's really for safety reasons. And that will confirm that it works. If you were to press the button, of course, and it didn't work, it would indicate this coil has gone open circuit, or the electrode in the ground has become disconnected or faulty in some way. Now the preferred way to connect these would have been to have the incoming supply here, and then the connection to the installation would be down here. Simple reason for that is if you kept the test button pressed in, or for some reason it jammed in that position, if your supply is coming in at the top, it will disconnect and then of course nothing will happen. However, if you had the supply coming in here and your test button jammed in the on position, the coil is going to be permanently powered, which is quite likely to overheating and smoke and flames coming out of the device. So this is all perfectly fine and nice, but of course there are some other things which can go wrong. Now here we've got a simplified diagram of a possible fault scenario. Got the transformer here, which generally be outside the property, 0 at the bottom and 230 at the top there. Line and neutral wires coming through. Of course the neutral is referenced to the ground as before. Line goes through into the property, and we've got here our earth leakage circuit breaker with the magnetic coil there and showing the switch in the closed position here. Now I haven't shown any kind of fuse box or other equipment or meter because that's not particularly important here. So we've got our line conductor coming through some kind of fuse into an immersion heater or hot water cylinder there with the heater in it, and of course normally the power would come in and return via the neutral back to the transformer. Now if something goes wrong here, such as this thing decides to short out to the metal casing of the water heater, typically made of copper, as that's connected to the earth connection here, that will put the voltage across that coil via the earth electrode back to the transformer, and that's what will trip out and disconnect the supply. So in this scenario that's perfectly fine, that's exactly what you want to happen. And of course that's the whole point of this device being here. But of course hot water cylinders don't just sit there on their own with no actual other connections. They obviously have water pipes connected to them. First of all, so you can get the hot water out of there, and of course so that cold water can be put in there, so that can obviously be refilled. This would typically come from a cold water storage system, which would be located generally in the roof of the property, and you'd have the pipe, let's do that in blue I think, just got the pipe there which would come down to the cylinder and generally go into the bottom. And there's your water in there. Now, nothing unusual about that, and of course from the top of the cylinder you would have pipes going off to your hot water taps, or maybe from the side there. Show that going to the hot water tap, and of course hot water will come out of there, no problem. Again, this is perfectly fine because that's just a bit of plumbing. The electrical part currently exactly the same. Now of course these pipes are actually metal, and it was quite often the case that the cylinder, or the cistern rather than the roof, would be metal. Galvanised steel would be a common scenario. The fact we've got earth connected here means that all this is connected to earth and all this is connected to earth, which is no problem. Again, if we didn't have this device, it would of course mean that your hot taps became live in the event of a fault, and that's another reason why these devices were installed. But of course this hot water cylinder and this cold water storage aren't going to work for very long in this scenario, because of course it's full of water, but it's not going to be full of water once you've turned the tap on for a while. So of course these things are filled from another pipe coming in here, and generally you have some sort of ball arrangement in there with a valve of some kind, so that as water drops it's filled in. And of course this comes from the cold water supply, which is typically provided through pipes that are buried underground, and that will go off to the water company, and probably miles and miles of this pipe through the street, supplying all the houses in your road. So that seems fine, but of course this is where the problems occur. Now the problem we now have is that when the fault occurs and the line somehow gets shorted through onto the casing of the material here, or the copper casing, some of the fault current will come through here and some of it will go via this earth path over here. However, because all of this is metal through here, and this is metal and this is metal, some of it will also go via the metalwork here and back into the ground over there. How much depends on the relative impedance or resistance of this electrode compared to the pipes here. Whichever has the lowest impedance is going to have the majority of the current going through it. Now if you compare this little piece of copper here, which might be say a metre long or something, poked in the ground, to what could potentially be many hundreds of metres of metal water pipes buried all along your entire street, pretty obviously the metal water pipes are going to have a much lower impedance, and therefore most of the current is going to flow this way via these pipes, and in fact very little is going to actually flow through here. This of course means that you have effectively shorted out the coil here via another metallic path. So with all of the fault current going this way, virtually none, or in some cases it could be none at all going this way, there's simply not going to be enough voltage across this thing to trip out the coil. So now you've got a situation where, although there's a fault here, and there could be dangerous voltages on this hot water cylinder, and of course the taps in your house and anything else that's metallic and happens to be connected to the installation, most of the fault current is going via the pipes here and over there. It's simply not going to be tripping out the device. This might as well not be here, because all you've done essentially is shorted out the coil. You might as well just put a wire across there, rendering it totally inoperative. And this is one of the major faults of these devices, that you've got other pathways to earth. This can be rendered totally ineffective, even if there's, say, dangerous voltages and things hanging around inside your installation. Now, obviously, these days you wouldn't have metallic pipes or metallic water system there. It would be made of plastic, but bearing in mind these things were designed 50, 80 years ago, when, of course, plastic pipes things hadn't been invented. And it's pretty much impossible in a modern house to prevent other paths going to earth, because as well as things like hot water cylinders, You're going to have things like central heating boilers, which of course use gas, which comes in via metallic pipes underground. They also have obviously water pipes connected to them, and of course they require electricity and inevitably will have an earth connection to them. There's also the situation, say, with your hot water cylinder. You've got a hot tap here, quite like to have a cold tap as well, and if it's in a metal sink, say in your kitchen, you've now connected not only via this path, you've now connected it via the kitchen sink, via the other tap on there, and of course that is going to come in from the same coal supply underground as the rest of it. So yet another example of a path there. Now another major problem with these devices is that they don't protect people from receiving electric shocks and potentially being killed. Now when these things were designed many decades ago, the vast majority of electric equipment would have had 3 connections: line, neutral and earth. Earth being connected to the metal cabinet of the equipment, so that if any kind of fault occurred inside, it would essentially short out to the earth and the current would flow via the trip device there and disconnect the supply. Of course today the vast majority of appliances do not have an earth connection. They're what's called double insulated or class 2 and only have the line and neutral. And of course there's far more stuff around these days, things which simply didn't exist sort of 50 or 80 years ago. So if you're cutting your hedge, for example, with your electric hedge trimmer, typically it's going to have the 2 wires coming in, and of course you accidentally slice through the lead, as happens on a regular basis. If you touch the end of this live wire, of course you're going to be standing in your garden, on the ground obviously, and if you sensibly pick up the lead and touch it, you're going to get an electric shock, because line coming in here goes into your body, goes through your body to the ground, and of course returns to the transformer over here. Now this device here is going to do absolutely nothing, because of course it's not even involved in the situation here. It's just sitting over here doing absolutely nothing. There's no earth connection here. All the fault current is going to attempt to flow via your body and continuing to do this until you've either disconnected it, or there's some other disconnection event occurs, or you're already dead. So in that scenario, this is going to do nothing at all. It's totally useless. And I say this could be a hedge trimmer, or in fact any kind of device. It doesn't have to be outside, because even if you're inside your house, the floor in your house is still going to be in contact with the ground there. So pretty obviously they're totally useless for that sort of situation, and they weren't really designed for that, to be fair, because say in the day most of the appliances would have had a metal casing, so that kind of situation probably wouldn't have occurred. And of course things like electric hedge trimmers hadn't even been invented. Now here's another scenario. People in general don't live in a street with only one house, although of course that can happen. What's more likely is that there's a transformer and it would supply a house here, and those wires will continue down the street to supply another property, and of course many properties further down the road. And of course they all need their individual electrodes, and they could be going on forever. Now assuming these electrodes are spaced well apart, it's not actually going to be much of a problem here. When there's a fault, say between the line and earth there, a certain amount of voltage will appear here, and as you move away from the electrode, the voltage will reduce. So at the electrode you might have quite a high voltage, and as you move away from the electrode that will fall away until of course eventually you get down to pretty much nothing. And the same applies on the other side as well. Now this is fine, provided that the distance between the electrodes is sufficient so that by the time you're getting halfway between the two, you don't have any of the voltage, or virtually none of this voltage, appearing at this point. In this diagram, of course, it's not a problem, but if your neighbour was a bit rude and naughty, and instead of putting their electrode over there, they decided that it was a bit unsightly, so they thought, oh, let's just put it over here. And they put it rather close to yours. That wire would of course connect in here. The problem we've now got is that when the fault occurs in this house here, yeah, the current will still flow through here, and this would probably disconnect, assuming those other problems hadn't occurred. But due to the proximity of these two electrodes, the voltage at this point is not going to be zero anymore, because simply the voltage being applied to this, and at that point say it might be say half of what we've got here. Now this can cause another unwanted effect. I mean, this is probably going to trip anyway at some point. Let's assume it probably did. But while it hasn't tripped, this electrode here, belonging to a completely separate property, is going to have some kind of voltage placed on it. Let's say it was half the mains voltage and we got sort of, say, 120 volts in there. Say it might not be there for very long, that will disconnect, but nevertheless it is in that position. So that means we've got 120 volts here. And if this particular property is one with the water heater in it and the metalwork and other things, which as I said is almost unavoidable, there will be, on this side of it, another path going to earth via pipes, who knows what. And if you've got a voltage coming in here, 120 volts, and that is fixed to earth generally far better than the grotty electrode in the ground, this is quite likely to trip because it's actually the voltage across it. Although it's in reverse, it's only a magnetic coil, it doesn't make any difference. So a fault in this house here could, in theory, trip out the supply in the house next door, or maybe the one further down the street. Pretty inconvenient. All right, they can go and switch it on again, obviously, but certainly it's not going to be what they want, and the fact that that's tripped in there might lead to people to think there's some kind of problem in their own house, when in fact the problem is next door. It's simply because these electrodes are placed far too close together. Now, of course, the obvious answer is to simply put the electrodes further apart. And if you put it in over here, then that's probably not going to happen. And it does require some other path at the other end, but as I've said, you can't really avoid that in modern houses unless you're not going to have any hot water or heating or pipes in your house. But of course, it's not quite as simple as putting these things further apart. If you lived in a row of, say, terrace houses, the whole house might only be, say, 3 or 4 metres wide. There could be a row of, say, 10 of them, all of which have to have their own electrodes, so it might actually be impossible to put the electrodes far enough apart to avoid this kind of voltage issue occurring. This, incidentally, is also why if you have an electrode in the ground, you need to make sure farm animals are kept away from it, because if you had a cow that stood here with its legs there, and of course it has legs over here as well, and there's the cow with no head. But the point being, if there was a fault, you might have, say, a high voltage here and a low voltage over there, due to the fact that the gradient of voltage slowly moves away. And then, of course, you've electrocuted the cow because there will be a current flowing through its front and back legs like that. As a small aside there. So that's a look at the earth leakage circuit breakers and how they fail to deliver in most common situations. I say these things don't protect people against contacting live wires. In many cases they won't work at all because you've got metallic paths to earth via water pipes, gas pipes and all kinds of other things in your house. The things themselves aren't exactly over reliable. And of course, if your electrode outside is positioned in proximity to one of your neighbours, you may find that faults in their property will disconnect yours and vice versa. Now these things were of course deleted from the regulations over 30 years ago, but sadly there's still a fair number of these in operation. If you do have one of these, make sure you get it replaced as soon as possible, preferably yesterday. Until next time, thanks for watching.